In section 3.4, we're going to look at the derivative of trig functions. But before we do that, what we're going to do is look at some special limits of trig functions. So that would be these two limits here. The limit as x goes to 0 of sine of x over x is 1. And the limit as x goes to 0 of cosine of x minus 1 over x is equal to 0. So from this first limit, we also get that the limit as x goes to 0 of x over sine is also equal to 1. So we're going to use these limits to evaluate other limits. In example 1a, we want to evaluate the limit as theta goes to 0 of sine of pi times theta over 2 times sine of theta. Well, notice that if I put in 0 for theta, we're going to get sine of 0 over 0, which is an indeterminate form. So what I'm going to do is, since sine is a continuous function, from our previous section on continuity, I can bring the limit on the inside and take the sine of the limit as theta goes to 0 of pi theta over 2 sine of theta. And now notice that the pi over 2 is just a constant. So I can bring that out in front of the limit. This will be equal to the sine of pi over 2 times the limit as theta goes to 0 of theta over sine of theta. And from the previous theorem that we just looked at, the limit as theta goes to 0 of 0 over sine of theta, that's equal to 1. So this will be equal to sine of pi over 2, and sine of pi over 2 is 1. So we can use those special limits to evaluate limits with trig functions where we get an indeterminate form. So sometimes they work, sometimes not. Let's look at another example. Notice in part B, if I evaluate this limit as x goes to 0, it would be sine of 0, which is 0, over 4 times 0, which is 0. And again, we get an indeterminate form. So in this particular case, what we're going to do is we're going to do a substitution. The problem that I'm having with this expression is the argument on sine. It's not just x, it's 3x. So I'm going to do a substitution. I'm going to let theta equal 3x. Okay, so notice that if theta is equal to 3x, if I solve for x, I get x is equal to theta over 3. So my goal with this substitution is to replace everything that has an x in it with theta, including that limit. Everything has to be in terms of theta. So let's think logically about what happens as x goes to 0. Well, remember x is theta over 3. So that will be going to 0. Well, if theta over 3 is going to go to 0, then clearly theta is going to go to 0. Another way that you can look at this is by multiplying both sides by 3, and we get theta is approaching 0. So now I can replace everything in this limit formula. I'll get the limit as theta goes to 0 of sine of theta over 4 times, now remember x is theta over 3, and let me rewrite that because algebraically that's a little bit messy. In the denominator I can bring out the 3/4, right, because we're flipping it, times the limit as theta goes to 0 of sine of theta over theta. And by our theorem, we know that this limit is equal to 1. So this whole limit is going to be equal to 3/4. All right, so what we're going to do in this next page is we're going to look at all the derivatives of the trig functions. And you're going to use these so often that it's just going to be natural for you to find the derivative of sine is cosine. The derivative of cosine is negative sine. Okay? And these are just derivatives that you just need to know. The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. The derivative of secant is secant tangent. And the derivative of cosecant is negative cosecant cotangent. In example 2a, if I wanted to find the derivative of this function f, I can do it in pieces, right? So, oops. So the derivative of f, so 8 times sine of x. Remember the 8 in front stays, and the derivative of sine is cosine. So this is going to be 8 cosine of x minus 4 times the derivative of cosine is negative sine. And then minus, this would be 5 times, and then we're using our power rule. We bring the negative 2 in front, x to the negative 3. Subtract 1 from the exponent. So let's go ahead and clean this up. The derivative is going to be 8 times the cosine of x plus 4 times sine of x plus 10. And here I'm going to go ahead and write this with a positive exponent. So 10 over x to the 3rd. All right, let's try another one. Okay, so here the derivative, I think I'm going to have to use the product rule, or the quotient rule, sorry. So we're going to have low to high, high to low. The derivative here would be the 1 plus sine of x, so that stays. And then I take the derivative of 1 minus sine of x minus 1 minus sine of x times the derivative of 1 plus sine of x. And that's going to be all over 1 plus sine of x squared. So that would be equal to 1 plus sine x times the derivative of 1 is 0. So the derivative of negative sine is going to be a negative cosine. Minus 1 minus sine of x. The derivative of 1 plus sine x, well, the derivative of 1 is 0. The derivative of sine is positive cosine. Okay, again, that's going to be all over 1 plus sine of x quantity squared. All right, so we're going to clean this up and multiply everything out to get a negative cosine of x minus sine cosine. And then it's going to be a minus cosine plus sine cosine and then that will be really nice because in the numerator some stuff will cancel. So notice that I have a minus sine cosine plus sine cosine that will go away. So I have negative 2 cosine of x over 1 plus sine of x squared. And there's no need to multiply out the 1 plus sine of x in the denominator. So this is where we would stop. Let's do more examples. In part C, I could do the product rule. Or, this is a really interesting problem. I could try to simplify this first. Because when you think about y, and you write everything in terms of sine and cosine, tangent is sine of x over cosine of x. So we're going to multiply this by sine of x minus cosecant is 1 over sine. So note if I were to distribute the sine cosine, I would end up with sine squared over cosine minus 1 over cosine. And now I'm simply subtracting fractions with the same denominator. So I get sine squared x minus 1 over cosine of x. Now you may think that this is worse, but it's actually not, because sine squared minus 1 is negative cosine squared. So going back to our trig identities. And this is over cosine. This would just simplify to negative cosine. And notice I still haven't even taken the derivative. I was just simplifying y. So if I was to find the derivative of y, the derivative of a negative cosine is a positive sine. So sometimes it's helpful to simplify expressions first, rather than jumping straight into the product rule. Something to keep in mind though is when you are taking these derivatives, it's expected that you're going to write it in the most simplified form. So why don't I go ahead and look at this by using the product rule. So you could see what it would look like. So if I was going to compute the derivative, I would take the derivative of tangent, which would be secant squared, and I would keep sine x minus cosecant x plus, because I'm using product rule, keep tangent. The derivative of sine x minus cosecant x would be cosine of x. And then the derivative of cosecant is a negative cosecant cotangent. So the minus becomes a plus cosecant cotangent. And I would have to write this in the simplest form. So typically when you have a large expression like this and you don't know if it's simplified, change everything to sines and cosines and see what happens. So secant squared would be 1 over cosine squared. And then in parentheses we would have sine of x minus 1 over sine of x plus our tangent is sine over cosine. And then in the parentheses we have cosine of x plus, so cosecant is 1 over sine and cotangent is cosine over sine. Now we already did this before and we got that the derivative was sine. This doesn't look like anything close to sine. So what I'm going to do is, inside the first set of parentheses, I'm going to combine these two fractions, so common denominator would be sine. I'm going to keep the 1 over cosine squared the way it is. I'm not going to distribute it. I could, but I can see algebraically that this actually would be nicer, because I'll get sine squared x minus 1 over sine of x. And remember, sine squared x minus 1 is negative cosine squared, so I can see that those things will cancel on the outside. And then here, if I distribute the sine cosine, the cosines will cancel in this first set, so that just becomes sine of x. And then also look, when I distribute the sine cosine here, it's going to cancel with the cosine sine to become plus 1 over sine x. Alright, so I get 1 over cosine squared x, and in the parentheses I'm going to have negative cosine squared x over sine. And then I'm going to keep the rest the way it is. Looking ahead, I can see how this first piece simplifies, because it's just going to be a negative 1 over sine, and it will cancel with the 1 over sine. So the cosine squareds cancel. This becomes negative 1 over sine plus sine of x plus 1 over sine of x. So the minus plus 1 over sine of x cancels, and we get the same answer that we got previously. In my eyes, I think rewriting and simplifying first and then taking the derivative was easier, but they're both kind of complicated. All right, let's look at our last example in this section. In example 3, I have y is equal to 2 times cosine of x minus 3 times secant of x. Part A, we want to find the derivative. And the derivative is equal to, the derivative of cosine is negative sine, so this becomes a minus 2 times sine of x. And the derivative of secant is secant tangent, so minus 3 secant tangent. And in this particular case, I don't think I'm going to bother finding a common denominator and seeing if it's in simplest form, because the actual goal of this problem is part B, to find the equation of the tangent line at pi over 4. So since we're trying to find the equation of a line, right, we need a point and we need a slope. Well, the point that we're using is x equal to pi over 4. And if x is equal to pi over 4, then the y value is cosine of pi over 4 is square root 2 over 2. So when I multiply that by 2, I get the square root of 2 minus secant of pi over 4 is going to be square root 2 over, square root 2. Yeah. So this is minus 3 times the square root of 2. So I can simplify that. That would be pi over 4 comma negative 2 square root of 2. I have a point. Now I need the slope of my tangent line. And the slope of the tangent line is going to be equal to the derivative, but we have to evaluate the derivative at pi over 4. So some people forget about that and I'll just plug the derivative in there. Oops, sorry, that's a negative 2 sine of pi over 4 minus 3 times secant of pi over 4 tangent of pi over 4. So again, we take the derivative, we evaluate it, and tangent of pi over 4 is just 1, so I can kind of ignore that. This is going to be equal to negative 2 times the square root of 2 over 2, which would be negative square root of 2, because the 2's cancel, minus 3 times the square root of 2. And I have negative 4 times the square root of 2. So we have our slope, we have our point. The equation is y minus a negative 2 square root of 2, so that would be a plus 2 square root of 2, equal to the slope, which is negative 4 times the square root of 2. In parentheses, we have x minus, and the x is pi over 4. So there's no point in actually writing this in slope-intercept form. But if you did solve for y and write it in slope-intercept form, it would be a negative 4 square root of 2x plus pi times the square root of 2, the 4's would cancel, and then minus 2 square root of 2. That's the best you can do. Okay, so that's it for derivatives of trig functions.